Hello, this is Siddhant Samant. We made a presentation on PUT Programmable Unijunction Transistor. Let's start with introduction. Programmable Unijunction Transistor or PUT is a close relative of a thyristor family. It has 4-layer construction just like a thyristor and have 3 terminals named anode, cathode and gate, again like a thyristors. Some authors call it programmable UJT because its characteristic and parameters are similar to that of a unijunction transistor. It is called programmable because the parameters like intrinsic standoff ratio, peak voltage can be programmed with the help of two resistors, wherein in UJT parameters like intrinsic standoff ratio, peak voltage are fixed and cannot be changed. The main application of programmable UJT are relaxation oscillator, thyristor filing, pulse circuit and timing circuits.
Hello, this is Lizanne and I'm going to continue now. So for the programmable unijunction transistor, now we are going to see the internal block diagram and the symbol. So as we can see, the PUT has a 4-layered construction, PNPN. And the topmost layer, the P layer, is called the anode. The N layer next to the anode is the gate terminal, and the P layer next to the gate is left alone. There's nothing over there basically, and the bottommost N layer is called the cathode. Now we're going to see like a basic PUT 2N6027. So this is how a PUT looks like.
Hello, this is Shraddha Sawant and I'll be continuing with the working of PUT, that is Programmable Unijunction Transistor. This is basically PUT biasing circuit. Let's go through the circuit and check the various components and their connections. So as you all can see over here clearly, the anode of the PUT is connected to the positive voltage, cathode is connected to the ground, and the gate terminal is connected to two external resistances R1 and R2. Now these two resistances R1 and R2 are being powered by external power supply, that is plus VPP. This full network, that is the gate terminal and the two resistance R1 and R2 together form a voltage divider network. At this point, it is also important to know that the value of these two resistances, that is R1 and R2, determine the intrinsic standoff ratio and the peak voltage of the PUT. Now what is this intrinsic standoff ratio and peak voltage? We'll come to know about this in the later part. Now that we know the various components and their connection, let's go and check what happens actually and how PUT works. Okay, so it has been initially what we do is we increase VA. VA is nothing but the voltage across the anode and the cathode. We increase VA, and it has been observed that as VA is increased, IA, that is the current across the anode, also goes on increasing. So as VA increases, IA also goes on increasing, and at that particular point the PUT device starts behaving like a typical PN junction. Okay, so as VA was increasing, IA also increases and the PUT device behaves like a typical PN junction. Now VA cannot increase beyond a particular point. At that point, sufficient number of charges are ejected and the junction starts getting saturated. That is, when VA reaches to its peak point, the PUT device starts getting saturated. Okay, now after peak point, VA goes on decreasing but IA continues to increase. In this scenario, that is, the VA is going on decreasing but IA still continues to increase, is called negative resistance scenario. And this characteristics of PUT, that is the negative resistance region, the negative resistance scenario, is been used in one of the PUT applications called as relaxation oscillators. We'll see deep about relaxation oscillators in the later part. Okay, so now we saw that initially VA was increasing and IA was also increasing, and PUT device started behaving like a typical PN junction. Further on, VA reached to a particular point, that was the peak point, and the PUT device started getting saturated. Now VA is going on decreasing and IA still continues to increase, giving rise to a negative resistance region. Now VA cannot decrease, VA can be decreased only up to a particular point, that is the valley point. Okay, so VA decreases up to a point that is called as the valley point, and the device becomes fully saturated and no more decrease in VA is possible. Now VA has decreased up to a particular point, that is the valley point, and the PUT device now starts behaving like a fully saturated PN junction. So this is how a PUT device is being converted into a fully saturated PN junction. Okay. Now that we know the working of PUT, let's go through the PUT characteristic curve. PUT characteristic curve is nothing but a plot between the anode voltage VA and the anode current IA. Okay, so it is the plot between the anode voltage VA and the anode current IA. Okay, it has been observed that it is easier to understand the working of PUT with the help of PUT characteristic curve. We can easily understand the working of PUT with the help of PUT characteristic curve. So let's see what happens in the curve and how it works. So as I have initially told you all, VA goes on increasing, and with that IA also goes on increasing, that is the voltage across the anode goes on increasing. Along with that IA, that is the current across the anode, also goes on increasing, but only up to a particular point, and that point is nothing but the peak voltage. Okay, so when VA is increasing, along with that IA is also increasing, in this particular region the PUT device starts behaving like a PN junction, and at this point, that is the peak voltage point, the PUT device starts getting saturated. Further on, PUT jumps into the negative resistance region, wherein VA is going on decreasing but IA still continues to increase. Okay, and after that VA decreases up to a particular point, that is the valley point. As I have told you all initially, it decreases only up to a point called as the valley point. At this point, the PUT device behaves like a fully saturated PN junction. Okay, so you all can see over here there is no more further decrease in VA that is possible. Okay, so VA decreases only up to this particular point, that is the valley point. Now it has been observed that we have been able to understand the working of PUT with the help of PUT characteristic curve. Okay, now next question arises is, can we find the value of the peak voltage, that is the VP? Can we find the value of the VP? Then the answer is yes, we can find the value of VP with the help of this formula. Okay, we can find the value of VP using the formula. What does it state? It states that VP is equals to 0.7 volts plus VG. Now what is this VG? VG is nothing but the voltage across the gate and the cathode. Okay, the voltage across the gate and the cathode. So it is given that VP is equals to 0.7 volts plus VG, which is also equals to 0.7 volts plus VR1. Now what is this VR1? VR1 is nothing but voltage across the resistance R1. Okay, so from the diagram it is clear that the voltage across the gate and the cathode will be same as the voltage across the resistance R1. That is the reason we replace this VG with VR1. VR1 is nothing but voltage across the resistance R1. Now to find the value of the voltage across this resistance R1, we have to apply voltage divider across this network. That is the reason we introduced the new term over here, that is 0.7 volts plus eta times VB. Now what is this eta? Eta is nothing but intrinsic standoff ratio, and VBB is the total voltage across the external resistance network. VBB is over here, you can clearly see it is the total voltage across the external resistances. And now what is this eta? Eta is nothing but ratio of R1 to the sum of the two resistances R1 and R2. Okay, eta is nothing but intrinsic standoff ratio, which is the ratio of R1 to the sum of the two resistances R1 and R2. What are these R1 and R2? R1 and R2 are nothing but the external resistances that we have applied. Okay, So if we know the value of this resistance R1 and R2, we can easily find out eta, and we know the value of VB. So with the help of that, we can find voltage across the gate and the cathode, and with the help of VG, we can easily find out the voltage VP. That is, VP was equals to 0.7 times VG. Okay. So by just knowing the values of this resistance and the power supply that we apply, we can easily find out the value of VP. Now what is the main advantage of PUT? As the name suggests, programmable unijunction transistor, it is programmable. Programmable as in we can change the output according to whatever input we are giving it. Okay. So what happens over here, it is clear from here that just by changing the value of these resistances R1, R2 and the power supply that we apply, we can get different values of VP. That is, the output curve that we get will change according to the values of resistances that we put in over here. So it is easier for us to get different outputs by just putting different values of resistance that are available with us. So this is a major advantage of PUT, and because of this advantage of PUT, it has been used in most of the applications. And what are the different applications and how they have been used, how PUT is used in those applications, we'll see in the next part.
Hello guys, I am Alpesh Sagar and now we are going to see the applications of an PUT. One of the major applications of an PUT is a relaxation oscillator. Now, the relaxation oscillator itself is used in many other applications like to produce low frequency signals for blinking lights, electronic beepers and clock signals. Earlier, PUT was used in deflection circuits and time basis for CRO. It was also used in voltage controlled oscillators, inverters, switching power supply, dual slope analog to digital converters and function generators. Now we are going to see the relaxation oscillator in detail. This is the circuit diagram of an relaxation oscillator. The only difference in this circuit is the introduction of R and C. Otherwise, the circuit diagram is similar as that was shown in the working of an PUT. Now we'll see the working of an relaxation oscillator. Here, the resistor R1 and R2 set the VP and the intrinsic standoff ratio eta. Resistor RK limits the cathode current to the PUT. Resistor R and C decides the frequency of an oscillator. When the VBB is applied to the circuit, capacitor C starts charging through R. When the capacitor charges through its peak voltage, the PUT goes into negative resistance mode. This leads to the creation of a low resistance path from anode to cathode. Now the capacitor discharges through this path. When the voltage across the capacitor falls below the valley point, the PUT reverses to its initial condition and there is no more discharging of the capacitor. So this charging and discharging continues and the cycle repeats itself. This charging and discharging of the capacitor results in the sawtooth waveform. This is how the waveform looks like. Now the frequency of the oscillator is given as F is equal to 1 upon RC log to the base 10 1 upon 1 minus n. Thank you.